Thank you. I loved at the beginning of the keynote session where there was this fantastic light show talking about how wonderful IMAX was, and what you get is me standing on a stage talking about garbage collectors with probably the most boring slides ever. So I was told apparently white is really harsh in this room, which means it's going to be really bright, and they asked speakers to use a dark theme, so I did this. Actually, I'm a little afraid. The tech people in the back, I think that's too high. I think they're not going to see the top third of my slides, which may be fine. Probably more boring content there, so yeah, that's better. Okay, I think this is going to work. So, trash talk. Why am I talking about garbage collectors? I lead the UI Toolkit team in Android. We work on animations and text and all the UI widgets and architecture components and the graphics stack that displays it on the screen, which has nothing to do with garbage collectors. But A, I think they're really interesting, and B, we talked about it at I/O last year, and I felt like something was missing, and I wanted to cover things in a little bit more detail. So we're going to attempt to do that today. I should also mention that the original idea for the talk was, okay, I wanted to explain why you shouldn't worry so much about garbage, and you should use the patterns and the APIs and the code and the objects that make sense to you in your code instead of doing old world Android performance coding, which results in really ugly performant code, but maybe you shouldn't worry about that anymore. So what I wanted to do was write a series of benchmarks and demo applications that would show this very, very clearly. And what I discovered is, oh my God, that is hard. It is really, really hard to do that because garbage collection is, by its nature, especially when it's working well, concurrent, which means you have no idea when things are going to happen, which means when you want to trigger the event, you won't. Also, devices change between releases, so it's really hard to compare things between the K release and the current O release or the past O release. Using emulators on the desktop is different than using devices. It's just a really hard thing. So I wrote some demos, and we'll see some of that stuff. But the talk evolved into one more of explaining why, going over the details of how the garbage collector has evolved and how you can take advantage of that in your application. So there is a common phrase in software. I assume this is also a common phrase in Ukraine. I haven't heard it here yet, but then I wouldn't understand it if I did hear it in Ukrainian. Garbage in, garbage out. But what nobody asks is, how fast? How fast does the garbage go in and out? So we'll attempt to discover that today. All right, so here's the history of this talk. A few months ago, I was at I/O giving a talk with Romain. Unfortunately, we were wearing sunglasses because the sun was unbelievably bright. So please excuse the sunglasses. And during the talk, we talked about memory. Right? We were like, okay, well, memory this, memory that, you know, don't worry about this thing anymore. And we gave some details, some of which I'll show here. So we said, okay, in the old Dalvik world, which is where a lot of our performance recommendations came from, the original runtime was optimized for size, so it wasn't really fast enough to do the modern stuff. The optimizations and the JIT that it used were not as powerful, so you couldn't really depend on that. In particular, allocations took a really long time, especially if you triggered GC for alloc, which is really slow. Collections took a long time, very non-deterministic. You ran into all sorts of problems. Sometimes you ran out of memory. Heap was fragmented, like all kinds of problems. So the recommendations for good programming on Android resulted in things like don't allocate ever. Use integers everywhere. No, ints. Don't use integer. Use int everywhere, right? Even if it's a floating point value, use an int. So just, do anything you can to avoid allocating an object. It's what we do in the framework code, and it's what we continue to do in the framework code because we are the inner loop. But also in your code, you should totally do this thing. And enums are evil, obviously, right? So never use these things. And then we had all sorts of interesting discussions online about enums, which went on way, way, way too long. And just primitive types in general. Don't use objects, use primitive types, because that's the way to really get the most out of Android. And if you look at a lot of our APIs, especially the APIs developed in the early days, it followed these patterns. There are enums nowhere in the old APIs, and everything is an int. If a method was going to return an object, then probably you would pass that object in so that you could allocate it and keep it around, as opposed to us having to allocate the object for you and then collect it eventually, right? So these were sort of solid patterns for years and years, and they made it into our documentation and our samples and onto Stack Overflow, which means that they will never die. All right, so now we fast forward into the world of art. This is the garbage collector that was introduced in KitKat. It was off by default, but it was on. It was the only garbage collector, the only runtime as of Lollipop, and it was written for performance from the beginning. We didn't have the memory constraints of the early Dalvik thing. You know, we didn't have only 192 megs for everything on the device, so we could actually spend a little bit more memory for things that we could do optimizations with. We had a JIT, but we also have AOT, right? It was AOT ahead of time compiled, so super fast to begin with, and then we introduced sort of a hybrid model over time, so we can JIT the code and then compile it offline. Allocation and collection were both faster. We defragment the heap for you, which has wonderful advantages all over the place, and then we have this separate allocation space for a large object. So all of this is really good. So the common patterns now are go ahead and allocate when you need to, use the proper patterns for your code. I'm even okay if you use an enum or two. It's okay, right? Now you should still be aware that phones are still constrained, you're still spending battery, and garbage collectors still are some amount of overhead. So be clever about when and where you do this, but in general, GCs work well. So that's what we said at I/O, and that was about all that we had time to say, but it sort of begged the question, why? Right? So we make a lot of claims on these slides, but wouldn't it be nice to back up the claims with more information? That's why I'm here today. So we're going to start with a little bit of discussion about memory and garbage collection in general. So let's suppose you have this super boring code down here. You have an int, and then you create an object there. Well, the int could go one of two places. There's a stack that is essentially free. This is compile time allocated. It says, I'm going to put this object here. It's essentially free, right? There's no collection, there's no allocation, it just sticks it there in some cases. So it's going to put that int over there, or it may put it in the register. Dalvik was actually a register-based runtime, so that it would actually allocate these things in the registers and move them around as necessary. Both of these are completely free. That is not what we're talking about today. What we're talking about today is heap allocation, right? So the heap is this extra block of memory that basically gets mallocked ahead of time, and then we manage on your behalf. When you allocate things, we stick them there. We don't know how that big they need to be ahead of time when we do the build, so we will allocate space for them and put them in the heap as necessary. So when you say new my object, it ends up somewhere in the heap, usually. Sometimes there's no room for it, and we'll get into that. But that's the general idea with garbage collection in general. It's allocating space for it on the heap, and then collecting it eventually when it's no longer used. So garbage collection can be explained in a couple of ways. Like, you already do garbage collection. If you're using a low-level language like C or C++, you basically need to take care of it yourself. So you've got this object that you allocate, and then you write some code that uses that thing that you allocated. That's great. And then eventually, if you don't do anything else, you're going to leak, right? Your process is going to get infinitely large because you're not freeing the memory, right? You are responsible for this thing, so you need to free it. So eventually you say, okay, we'll delete this thing. Well, then what if you actually go ahead and use the thing after you've deleted it? Well, then you will crash, maybe. And this is one of the most evil things to track down ever, is a referenced freed object, which non-deterministically will crash your program somewhere, and it's going to blame it on the wrong thing, and then you spend the next several weeks trying to track down what the problem is. So garbage collection, when you're doing it manually, C, C++, level languages, tends to be really tedious. You have full control over everything, which is great, except you are responsible for everything, which is not so great. So then we move to higher level languages. So here's an example from Java doing something similar. You're going to allocate this object. You're going to write some code that uses that thing. And that's all you need to do. Eventually, we're going to free it on your behalf. That is what the runtime is for. It will notice that it's no longer being used. And eventually, a garbage collection will run and free it on your behalf. Or if you keep using the thing, we will also notice that, which means we're not going to free it ahead of time. We're going to free it when you eventually stop using it. So there's no leak. We will free it eventually. And there's no crash because we're not freeing it before you stop using it. OK, so let's talk about the runtime. There are several questions that come up if you're thinking about runtimes, like how long does it take to actually allocate an object? How long does it take to essentially do our own version of malloc inside that heap, right? We need to find room for it in the heap, find a place to put it, and then squeeze it in there somewhere. So how long does the allocation take? How long does a collection take? And what implications does this have on the other thread? So when we are doing a collection, especially if it's happening in the background on another thread, well, what's happening to the rest of the system? right? Or if we happen to run a collection while you're trying to do something on the UI thread, the most obvious example is if you've ever seen in the log GC for alloc, it means that you tried to allocate an object, it couldn't find room, so immediately needed to do a full collection in order to get things out of the heap so that it could make room for your object. Tends to be very expensive, so you really care about how long the collection takes because you're stalling the UI thread and creating jank for the user at the time. And when do these collections happen? Do they happen like while you're trying to do something on the UI thread? Do they happen in the background, but while something else is happening, which means you're going to get a stall in some other part of your process? And how efficiently are we actually using the heap? Are we going to fragment this thing? Are we going to take up a lot of memory for your process, even though you're using a very little amount of it? And this ends up affecting the entire device because all of these applications are doing it across the entire system, including the system process and the system UI and GMS core. These play services, these long-running processes are going to be taking up these large heaps, which means that you need a lot of memory on the device to have a decent user experience. So we'll attempt to answer some or most of these questions for the various versions of the runtime that we've had on Android through the years. So this is an example of Dalvik. I'm leaving out some of the details in terms of exactly what the heap is structured like, but this is sort of a good overview of it. We have the blue object up here is the object that just came in. It needs an allocation, right? The user code, the application code has said, I want to create one of these things, so we need to find a space for it in the heap. So where are we going to put it? The allocation process essentially looks like this. It walks across the heap, and hopefully eventually finds a place to put it and slides it into place. That's the best case scenario. It didn't actually have to walk very far, found a place for it that was large enough, and it stuck it on the heap. That's great. And then eventually we collect these things. This is a several phase process. Is the concurrent marked sweep collector that was in Dalvik. We mark the root set. We essentially say, okay, which of the objects in the heap are referenced, like directly from application or system code? And this is something that requires a pause. This is part of the expense of the collector in Dalvik was it stops the world. It stops your UI thread. It stops all other threads in the system because it can't figure out which ones are referenced unless it stops everybody from referencing anything new. So it stops the world, and then it says, OK, which has a reference back to the root set. And then it marks the ones that are reachable from those. So it's either referenced from the root set or it's indirectly referenced from one of those objects. So it'll mark all of those. So now it's figured out in the heap which are all the objects that are live, right? And it wants to collect the ones that are not live. Now, while it's doing this, something else may have been allocated in the meantime, so that one just appeared in the middle. So while that concurrent thing was going on, someone else required another object to be allocated, so it's stuck in the middle of the heap. So then we have a second phase, which is also a pause, and it goes through the heap again and says, okay, now what are all the things that got allocated in the meantime, so that we can track everything in the heap that's been referenced, so that we know the exclusion set of that, everything in the heap that is not referenced anymore. Then we mark those items. You can see them grayed out there on the slide. And then we have a collection phase, which is concurrent, which means it doesn't need to stop the world to do the collection. So that's good. So this is the best case scenario. This is sort of typical GC behavior when you're allocating and collecting. Okay, so let's take a look at a couple of other scenarios. So here's this object we want to find space for. If you look down there at my incredibly complicated diagram, you will see that there is not space enough in this really complex and beautiful heap for the blue object. So what are we going to do? We're going to walk the heap. We'll walk around, we'll look, and we'll get very frustrated because there's no room for it. So this forces a collection. So this is a GC for alloc. This is the really expensive one, especially on Dalvik. It's not as expensive on Art, nor should it ever even run in most scenarios. But in Dalvik, it was very common because all this stuff would be there. You would try to make room for a new object. It wouldn't have room, and then it needs to force a collection immediately, which is going to take anywhere from like 10 to 30 milliseconds. So you're basically going to jank at least one frame whenever you run into this situation, which is quite common. So then it forces a collection, it gets out all the things that are no longer referenced, and then it does the heap walk and allocation again, finds a space for it, and slides it into place. All right, so again, sort of best case scenario, at least there was room in the heap for it. Here's another scenario, which is unfortunately common as well, especially in large applications that have allocated a bunch of stuff over time. There's the heap. There's nothing that actually isn't referenced anymore. It tries to find room for it, and it can't. So then what? So there are two things that happen. Either it can grow the heap. So this is a common way out of it. You start with a relatively small heap from Dalvik, and then it'll grow it over time. So if it runs into the situation, does a GC for alloc, can't find room, it'll basically add memory all the way up to the max memory for the processes, whatever that is on the particular device and release that you're using. So it'll grow the heap typically, or if it's already done that and you're using max heap on the device, you're out of luck, and then you're going to get an out of memory error. Right? So this is terribly unfortunate. It doesn't happen that often, but it is possible because we have this situation of heap fragmentation in Dalvik, which I'll get into a bit more right now. So fragmentation on KitKat, I wrote this amazingly complex demo. I'll describe it here. It allocates an array of objects of 1 megabyte each until the full extent of the heap. So it grows the heap up to the max and basically allocates the hell out of it, right? Fills up the entire heap with these 1 meg chunks, and then it goes through and nulls out every other one so that I know that half the heap is free, but in this interleaved fashion. So here in the starting screen of my really complicated app, it says, you know, heap size is 399 megs, and then you press the allocate button, and this is what the heap looks like after that. All right? And then we go to the second screen, and it says, okay, now fragment the heap. So it says there's essentially 1 megabyte left, sort of, you know, here and there in the heap. But then it goes through and frees every other one. And then you get the following screen. It says, okay, now there's 200 megs free, which is great. So what I want to do now is I want to allocate a 2 meg object. So that little blue square down there, okay, the size isn't quite right, but it's supposed to represent this 2 meg object that I want to find room for. Well, there's 200 megs in the heap, right? So surely somewhere in there we could find room for it. What you get instead is a crash. Right? So this is the fragmentation problem on Dalvik. Even though there is 200 megs free, there is not a contiguous 2 meg chunk in which to stick that block. So it's going to walk the heap. It's going to do a really expensive collection. It's doing this GC for alloc, trying to get rid of stuff, but it can't get rid of anything that is large enough to find a slot for that little blue object. And our sad blue object causes the application to crash. And this is what the logcat looks like. I don't know if you've ever seen this one. This is, I find this amusing. It says, okay, on the first line it says, I have basically almost 200 megs free out of a total of 400. So things are looking pretty good. And it's going to force a collection for this 2 meg object. This is all very straightforward. That didn't quite work, so it's like, no, I still have 200 meg free out of 400. So I'm going to do this final GC before I run out of memory. And then it says, no, actually you're out of memory for a 2 meg allocation when you have 200 megs free, which sounds ridiculous, but it is the fragmentation problem, which we have now solved in Art. So Art, as I said, was introduced in KitKat, but it became the only runtime available in Lollipop. Many things are good about Art. One is that allocations and collections and just the basic code is faster using AOT, and also a lot of the optimizations that were built in. The other nice thing about Art was it was built from the beginning to be a platform for optimizations. Dalvik had gone about as far as it could as far as optimizations. Art enabled much more, and in every release since Lollipop, they put in more and more things like inlining and escape analysis and all this sort of really good runtime stuff that they could build in there because Art enables it at its core framework level. All right, so here's what allocation looks like. In Art, they developed this new allocator, so instead of using dlmalloc, they have this thing called roast alloc. It does thread local allocation, so it eliminates a lot of the pauses because now the threads can just allocate on their own without pausing the rest of the world. It has this system of grouping allocations, which makes it a lot more efficient. So if you're a small size, it's going to put you in these page-sized regions and allocate those things together. And then if you're a larger size, you're going to end up in a page-aligned section all on your own. Finer grained lock, so you're no longer locking out the world. Instead, you're just locking, you know, the little region of code that you need to do these things. And it ends up being about 4 or 5 times faster than Dalvik for allocations in particular. All right, so here's what a similar thing looks like in Art. For large objects. So we had that situation before where like you have to fit the large object in among everything else in Dalvik. It was just one contiguous heap where everything needed to live. One of the nice things about Art was we have this concept of large objects that are going to live somewhere else, which helps a lot with fragmentation. So you're no longer fitting everything in there, and then you need to find space for huge objects in among all these interleaved tiny objects. Instead, all the big objects go somewhere else. In particular, we just malloc them on their own. Right, so we have this large blue object. Oh, actually, this is the small case. Okay. Yes. Large blue object that we want to fit somewhere in here. It doesn't look like it's going to fit in there, but we don't care. In Dalvik, what we needed to do is try to fit it in there somewhere and then force a GC for alloc, grow the heap out of memory, whatever is going to happen there. But in art, we basically just stick it somewhere, right? So it is still counted as part of the overall heap size for the process, but we just malloc space for it. This is specific to particular kinds of objects. We can't have these objects referencing other objects, so they are only for primitive arrays and strings of sufficient size. I think the current heuristic is about 12K, which is about 3 pages. They may change that over time, but basically it's incredibly cheap for us to do this, and it doesn't cause this heap fragmentation as well as more process time for finding future allocations because all these things just live on their own. We also have a moving collector, so now we can actually defragment the heap, which was so key to avoiding these out-of-memory situations. So there's no more fragmentation. Eventually, in Lollipop and up until the O release, we would defragment in the background, which meant that when you're in the foreground, we're not going to defragment, but eventually you're going to go in the background, some other app is running there, and eventually during some idle time, we're going to defragment. This is because it's a fairly expensive operation, so we don't want to jank your app just to collect your heap for you. So we would do it eventually in the background. However, we also do it in the foreground when necessary. I learned this when I wrote my demo application to show this. I wanted to show, okay, well, fragmentation causes crashes in KitKat and also all the way up to O because we can't defragment except in the background, and I was wrong. GC for alloc will actually force a defragmentation because it will find space for it if it's possible. So we'll see that in a minute. Okay, so in Arch, yeah, basically we can take all those little chunks and then just collapse them over there. I'm going to show this in a little bit more detail later. All right, so this fragmentation example I showed earlier on Dalvik looks like this as a Lollipop and forward. So we have the initial starting screen. We've got about 400 megs free, and then we're going to allocate the heap as we did before. Looks exactly the same. You know, in theory, this is a very coarse-grained view of what's going on. It says, okay, there's essentially 1 megabyte free, you know, here and there in the heap. So go ahead and fragment it. Again, we're going to interleave the frees, null out every other one, and we've got 200 megs free over the heap overall. And then we're going to try to find space for this chunk in there, and it'll actually defragment for us, collapse everything, and find space to squeeze that thing in. And now it says, yep, you still have 200 megs free because it's already defragmented the heap on our behalf. So this is what Dalvik GC looked like with marking from the root set and all the reachable objects. There were 2 pauses there that resulted in about 10 milliseconds of delay during a typical GC. And we've eliminated that down to 1 pause in Arch. So there's only 1 pause, that second pause, which is much faster. So we can do the initial marking concurrently, and then the other one is much smaller, takes about 3 milliseconds. So much faster to do this stuff, and much more stuff is actually happening concurrently. So a few things worth noting about art collections. The minor GC kicked in Lollipop, and I'll get back to that shortly. It's not there in the current releases, but will be there in the future. We noticed that objects that would get allocated and then dereferenced very quickly, these temporary objects, if you just allocate it in the scope of your method and then you return from your method, we can collect those very fast. So we have a minor GC that will only look at those items that appeared since the last real GC. And we can collect those incredibly quickly, so we don't have to walk through the entire heap. We just walk through the smaller subset of these temporary objects. Large object heap causes less fragmentation overall because now we take all those large objects that don't reference anything else and we shove them somewhere else instead of interleaving them in with all the tiny objects. There's also less heap resizing because if we're not fragmenting things, if we're not stuffing everything in this one contiguous heap, then we don't need to constantly resize the heap to find more room for all the objects of different sizes. And there's fewer GC for alloc pauses because we don't have to find room, right? So we take all the big ones, we shove them somewhere else, and then it's easier to find room for all the smaller ones in the large contiguous heap. Faster runtime, just by nature of what art was, the ahead of time compiles, as well as the JIT plus AOT hybrid mode that came in later. So in Marshmallow, there were some various compiler optimizations as well as optimizations for allocations. In Nougat, there was, again, we just keep doing more and more optimizations in every release, so things are faster in general. Allocations were rewritten in assembly, and now we're seeing about 10 times faster in allocation performance in Nougat compared to the last version, Dalvik, in KitKat. In Oreo, there was a huge change. So now we have something called the concurrent compacting collector, and now we can actually compact the heap in parallel with everything else. So we don't have to wait until we're in the background, and we don't have to do it synchronously when we're doing a GCU for alloc. Instead, there's just this thread running in the background that will occasionally move stuff out. I'll show you a diagram of how this happens. So now there's less heap resizing and fewer GC for allocs, which is awesome because these were real performance hits. Instead, we're just constantly compacting. We don't need to keep growing your heap because we can keep making your heap very optimal to put new stuff in without just adding more space onto the end of it. This is really good for the overall device because it means not only is your application experiencing a smaller heap, but all of the other applications are as well, including system-wide and long-running processes like the system server itself, or Play services, or the system UI. These are processes that start when the device turns on, and they just keep running. So if we only defragment in the background, then guess what? We never defragment those unless we need to do like a really expensive GC for alloc. But as of O, now we can defragment while it's running in the foreground, which means we keep their heap sizes smaller, which means all process heap sizes are smaller on the overall system. So here's a diagram from one of the art talks, I think at I/O a couple of years ago, where we can show actually heap sizes on Android in general were 32% smaller just because of this dynamic. So concurrent compaction looks like this vaguely. Again, details are a little bit sketchy, but we've broken up the heap into all these regions, and the regions can now be assigned to individual threads, which is much more optimal because now a thread can be given a region. It only needs to pause itself. It's a thread local allocation, so it's going to allocate on its own without pausing the world to do this. Doesn't need to communicate with anyone else. It's only responsible for its own region. Right? So in the compaction phase, we will notice that there are regions with less than, I think the heuristic is 70 or 75% allocated, and then we'll empty those regions and put them somewhere else. So we'll take all the ones from T1 and T2 and T3 regions and put them somewhere else in the heap, which means all three of these are empty. And now we can do something really fast, which is thread local bump allocation. So instead of walking the heap and finding a spot for it, which tends to be really expensive and also tends to scale proportionally in time with the size of the heap itself, the size of the lives of objects, instead we can just bump a pointer in there and say, okay, I've allocated an object, the next object is going to go right next to it in that little region specific to that thread. So much faster allocations, and now we're up to 18 times faster than Dalvik in that release. Let's see, so here's how allocation happens. So you can see this visualization here where we have these little objects being tossed into the regions here. If we take a zoomed in view of this T1 region, those objects got allocated like this. We had the first one, we just moved the pointer. Second one, third one, fourth one. Very, very cheap and fast, which is good for you. So here's a diagram of how the speed went over the years. So you can see, like, you know, through the assembly optimizations and all the other optimizations for allocations over time, things are better, which is good. All right, so where are we going in O? So the collections, as I said, the young collections for temporary objects are gone because we basically rewrote the entire collector. So there's a lot of other advantages. Performance is still really good, but this is something that we would like to reintroduce to the new collector. So that code is actually checked into AOSP. I'm sure all of you are monitoring AOSP art improvements on a continual basis. So I'm sure you've all seen that. So that's in AOSP, so I'd expect that in some future release. So one other note I wanted to say was about object pools. It is common practice to use object pools because everybody knows that reusing objects is faster than reallocating them because you're going to have the overhead of allocation collection. And this is true in a gross sense. So if we see this graph on 7.1, you can see let's see, blue is normal, pools, right. So on this particular release, on that runtime, you are always going to spend more time doing garbage collection and allocation than you will simply reusing these objects, depending on what the objects are like. But it is a practice that people use. It's a really complicated process. We would like you to not have to do that because it's tedious to manage these in a correct way. But we ran benchmarks recently internally, and it looks more like this. On Oreo, because collections are so fast and happen concurrently, then especially if you're using synchronized object pools, then there is this trade-off in object size. I forget what the size is exactly, a couple hundred bytes, where it just doesn't make sense for you to manage the objects because actually the GC is faster. It's important to note that this is comparing itself to synchronized object pools, and there are better ways to do object pools, but again, requires a lot of tedious management. The advice is this is a really hard thing to do well, so maybe you could actually just trust the garbage collector to do it for you now. So what is the advice now? Where do you go with all this stuff? So it's all the stuff that we said in I/O. Basically, garbage is okay. Both allocations and collections are significantly faster. So if you want to allocate that object, even if it's an enum, that's okay, right? But it's important to note that GC still is overhead. We are running code, which means we are taking up processor time and battery. So if you're in critical code, if you are in an inner loop, then maybe there's a better way to do that than allocating an object all the way through, because you are causing some amount of overhead. It's just not nearly the amount that it used to be. But still try to avoid it in the inner loop. As I said, in the framework code, we tend to still write this very performant code because we are the inner loop of all of the applications. So I have a demo. Let's see. I think I still have a couple of minutes. That sign says I have 5 minutes, which means I'm going to make a grave mistake here and try to run a demo that shows some of this stuff. So I wrote this jank test, which I'm having a really hard time getting crisp results out of, but we'll see. We'll see how this goes. OK, so the emulator on the left, this is KitKat, and this is O. So this is an Oreo release on the right. This application has this little bouncing square. I love this because it reminds me of Breakout, which was my favorite game when I was a kid. That should tell you how old I am. OK, so I notice in the rendering when we've janked a frame, when we spent more time doing stuff than we should have, then the green square is going to flash red for just that one frame. It's a little bit hard to catch. And it's not janking right now. We're not actually allocating anything. We're not doing anything expensive. But if I turn on auto boxing here, which is basically I'm allocating a bunch of floats in the background, and every frame I'm allocating an array. It's sort of a ridiculous canned example, but I'm allocating a bunch of float objects, and these floats are being turned into capital F floats because I'm storing them in some object collection. And then we end up with this kind of output. So you can see it occasionally janking, turning red there. The line on the bottom, like the green line, is kind of where you want to hit for frame time. And then the spiky vertical line is showing the actual delta between these frames. And if you look at the output, we have a bunch of GC for Alex, right? So in generally, the time spent in just allocating the objects, stuffing these primitive floats, auto-boxing them and stuffing them into the array takes 1 to 2 milliseconds on a typical frame, but then occasionally we trip the bar, we cause a GC for alloc, and then we hit a frame time that causes us to jank. So there's 12 milliseconds. Here's a delta time between frames of 47. Here's 41. Here's an alloc time of 11 milliseconds caused by the GC for alloc. OK, so that was KitKat. Oh, and you can see I'm printing out the jank percentage here. So about 3% of the frames overall are janked. We're basically missing a frame in there. So let me stop this one and go to Oreo and hope very desperately that this will demonstrate what I'm trying to demonstrate here. So we start out with no problem there. We're not allocating anything. And then I go into the auto-boxing example, and you can see not really a problem. Now, when this goes in the background, it tends to cause processor problems. We'll see how this goes. All right. So here we are. We can see, OK, so it does jank occasionally. It's not perfect. Again, it's a very canned example where I'm doing these thousands of things here. But we can see the allocation times are sort of 0 to 1, and we don't have any GC for allocs, right? We manage the heap much better, and we do it concurrently, which means you're never really in a real situation. You're never in the state where I want to allocate a thing, and therefore I suffer a major garbage collection event in the meantime. So yay. And then another part of this example is showing bitmap allocation. Same thing, except I'm allocating a chunk of like a, 250 by 250 bitmap, but that is not really showing what I wanted to either. Yeah. Emulator. OK. Yeah, and this is like processor the speed of my MacBook Pro as opposed to those devices. So again, not a great situation. But in a typical situation, you could also see a lot of jank there on K versus O, because on O, all we do is stick it somewhere in the heap. It's a very cheap operation. All right, so finishing up here, you can see the outputs here. I recorded in case the demo didn't really work. On the bitmap side, I was seeing in the situation I had before, sort of an allocation time of 10 milliseconds, and then a bunch of these GC for allocs dealing with these large objects that on O we could just stick on their own by doing a simple malloc. And that is all I have. Thank you.
Hi, I'm Julie.
And I'm Safia. Today we're going to talk about digital well-being. As researchers on the Android team, we have been studying smartphones and the impact on people's ability to manage their attention throughout their day. Last year, we spoke to some feature phone users in Japan who were avoiding using smartphones. We noticed how happy they were and how they felt in control of their time spent on devices.
Instead of FOMO, or the fear of missing out, they were experiencing JOMO, the joy of missing out. The joy comes from feeling in control, and it doesn't feel like they're missing out on anything.
We decided to dig deeper into how users might have trouble disconnecting from their smartphones and why it's difficult to disconnect. We learned that mobile innovation has made smartphones indispensable. Essential functions bind people to their phones, like communication and navigation.
It's hard to disconnect from your smartphone because you still need to use these things. With the phone so omnipresent, there are some negative consequences. We found 2 negative behavioral cycles. The first one is an internal challenge with habit and self-regulation.
People notice their behaviors evolving over time, experiencing phantom cues from their phone, repeatedly refreshing an app, hoping for new content, and contributing content to manufacture new triggers.
The second cycle is an externally reinforced cycle of social obligation. There's a shared expectation of being available to others 24/7 and to respond quickly.
The sender may experience anxiety while waiting for a response, and the receiver may feel pressure to respond quickly. So it's hard to disconnect from your smartphone because there are things on it that you need, things that you enjoy doing, and you might need to reply to someone quickly.
A user told us it's like a prison. You can get lost in your phone and not get out. Gaming, social networks, being available to others all day, you can't get away.
At Google, we're committed to giving everyone the tools they need to develop their own sense of digital well-being. This means helping users understand how they interact with technology, focus on what matters to them, and switch off and disconnect when they want to. How are we doing this?
Our approach to digital well-being includes 3 important pillars: awareness, control, and responsible design. We believe that user awareness is the first step. The Digital Wellbeing Dashboard gives users an overall awareness of their daily phone habits. With awareness, users can begin to consider whether their usage aligns with their personal goals.
We're also giving users control with tools that will help them practice their desired behavior. App timers allow users to set daily limits for each app, which block access to the app when time is up.
The wind down feature helps users disconnect in the evening by visually changing how the phone screen looks, like fading it to black and white with the grayscale feature. The wind down feature also helps limit distractions by turning on Do Not Disturb.
We are actively exploring more ways we can design responsibly to respect users' attention. We encourage developers to consider how you might provide users more awareness of their behaviors. Consider how your products might contribute to the 2 negative behavior cycles, and explore the indicators of user value aside from engagement. Together, we can work towards the joy of missing out,
so users can feel in control of their actions and happy with their smartphone use.
Thanks for listening.
La charla que voy a dar más que todo es sobre mi rol que hago en Google ahora, que es software engineer. Trabajo para el equipo de Google Play, en equipo en Londres. Y más o menos tengo trabajando en Google hace poco más de 3 años. Antes trabajé también en San Francisco, ahora estoy en Londres, en el equipo de Google Play. La charla del contenido es, voy a hacer una introducción sobre la empresa, sobre la cultura de la empresa. Después voy a hablar sobre, vamos a tener un juego, donde voy a regalar un polo de Google que he traído de un swag de Google. Y bueno, después va a haber más contenido de los proyectos que nosotros buscamos hacer y cómo desarrollamos un proyecto en Google en sí, ¿no? Ok, empezamos. Aquí tengo el pasador. Ok, esta es la agenda. Como les comenté, la intro, lo puedo ver yo. Es muy alto esto acá. La introducción, como les comenté, ya la introducción que la que hice ustedes, un calentamiento que va a ser un juego que vamos a hacer. El rol de SETI, que es Software Engineer Tools and Infrastructure, en Google. Los proyectos que hacemos en Google Play. Y algunas preguntas que ustedes tengan, ¿no? Las preguntas pueden ser en forma general, tanto de Google o del Google Play o cualquier cosa que se les venga en mente durante la charla. Un favor sobre la audiencia. ¿Quiénes son estudiantes? ¿Pueden levantar la mano? ¿Cuánto reduce el APK el nuevo modelo de Android App Bundle? hasta un 25%, hasta un 35%, hasta un 45%, hasta un 65%. ¿Cuánto se reduce la aplicación si usas Android Add Bundle en vez de una APK tradicional? Hasta un 65%. El podio, Gonzalo. Gonzalo adivinó las últimas dos preguntas, creo. ¿Quién es Gonzalo? Vamos a ver, me parece tu premio.